Yeah, so I'll talk about my experience trying to use Legate as a backend client for JAX. I say the framework formerly known, which I will get into why it is no longer Legate JAX. So the sort of missing capability in JAX is kind of the general framework. You'll see different terms. I like the terms intra and inter-operator parallelism. We have some task graph that's a bunch of math operations. You could choose to execute that operation by operation and say, I'm going to parallelize each of those operations individually using sort of data parallelism within them, the intra-operator way. Or you can say, maybe there's some parallelism to be exploited where I'll have different submeshes executing different operations, right? So sort of task or MPMD parallelism. Or you could mix the two, which is kind of the main way that pipeline parallelism is done today with training LLMs. So that sort of intra-operator way is the only way that JAX natively supports. You can say, I want to parallelize an operation, but you can't really place different operations across different submeshes. So our goal when we started this was we want to target, really large scales. So we like the fact that the realm execution model sounded great. You want to keep your device executing all of these critical path tasks, enable this asynchronous communication and other small sort of tasks that I want sort of host-driven off critical path. The Legate programming model sounded great. It actually makes some of these very complicated patterns very easy to express. So there's these like 1F1T schedules, there's load balancing of stages, all overlapping communications. I don't need to worry about any of that. I just give it a sequence of tasks. And then I tell the mapper where to place them, and I'm done. All of the event graph construction and all of the asynchronous execution is taken care of for me. There was another layer to this. I'm not really going to focus on kind of what we've done with XLA and JAX. I'll focus more on the runtime pieces. But that was another component. We did have add some stuff to JAX to actually make it possible to express these because there was no API even for expressing it. And for those who maybe don't know LLM training, so pipeline parallelism is kind of the main thing that we're trying to support. And the idea being that you feed in these input batches, and then they kind of pipeline through the different GPUs to different transformer layers, and then there's the backprop where you get all the gradients. And so you have some bubbles in there. If you have a really deep pipeline, then these bubbles become kind of negligible. But again, rather than trying to parallelize each of these transformer stages over all of the GPUs and kind of executing them one by one, you say, oh, I'm going to put different layers on different GPUs, and I'll just pipeline the different data inputs through them. Okay, and that, like I said, that's MPMD parallelism with exceptions for specific cases. So okay. So I talked about how this all looked great, like Realm and Legate sounded great. In particular, they sort of share a core philosophy. So when you're writing JAX code sort of in your SPMD style, you just write like sequential NumPy code. And then there's this compilation where you generate your device code, but it's just sequential code. You define the model. There's nothing complicated here. It's just like standard NumPy code, kind of similar to like CuPy numeric stuff. And then I go back through it and I add sharding annotations. And I describe how I want my tensors to be sharded. The sort of easiest way to do that is I assign names to the tensor axes. And then I define a device mesh and I say, well, okay, I want to, create this 2x2 device mesh, and I'm going to match now these names I defined before to the actual physical mesh. I'm going to and this and it inserts all the data collected, et cetera, needed for SP. This is exactly Legion, just kind of in Python in a different context, right? You write sequential code, you define partitions on your tensors, and then voila, the runtime system. Build a parallelism. So like I said, kind of going back, this is kind of like the deprecated PJIT way of writing it. It's just kind of easier to present, but there's a new JIT. But generally speaking, you have to have a uniform global mesh across all of your tensors, right? This is this intra-operator restriction, only SPMD. So very briefly, we added some extra from APIs. So now I can have this like task modifier I can add to these functions. I can place them on different meshes. I have to call this slightly separate parallelized function as opposed to the standard JIT. But this will now generate a slightly different task graph that gets fed to the back end. And this will dispatch these different pieces to different submeshes. So I can construct a pipeline doing it this way. So yeah, so sort of phase one of this is there's, like I said, there's a whole other JAX, MLA, XLA stuff that I'm not going to touch on, but there's a bunch of compiler pieces that take the graph generated from JAX, it turns them into Legate, I should say Legate tasks. And then right, you map the pipeline stages to the different submeshes that you sort of described in your application, and then voila, I have pipeline parallelism. Okay. And we wanted to do sort of more interesting things than just, okay, we'll replicate the existing pipeline parallelism solutions. So an example of something sort of more interesting and complicated that we wanted to do. So generally speaking, you see these pipelines drawn out and they're always these nice figures with exactly balanced layers and exactly sized correctly. But the reality is you have some extra like little things like these embedding and logits that go at the beginning and end. And they can kind of foobar your pipeline to the amount of like 5 to 10% load imbalance. So usually people just throw them on GPU 0 and the last GPU. We said, okay, well, what if we kind of come up with a load balancing scheme and we'll move them around and have all the GPUs executing them. And it's sort of particularly annoying in backprop because you have your gradients being sort of collected and summed on different places. You have other GPUs that are sort of eagerly starting these extra tasks and sending them back to GPU 0 to restart the pipeline. So it's kind of complicated to do. But not with Legate. So basically, like I said, there's XLA compiler magic. They spit out these tasks with the mesh assignments. I have some scheduler that says the order that I want to execute these in. That's this 1F1B versus G-type schedule, which I don't really have time to go into. And then all I need to do is I just loop through. I assign a scope to the mesh. I create the task. I add the inputs and the outputs to it, and I'm done. Right. And if I have sort of chosen to assign my stages in kind of a load balanced way, that's just taken care of for me, right? Load balancing kind of comes automatically. So it's not load balancing kind of in the dynamic runtime sense that is commonly used with Legion. This is sort of like the compiler sort of statically chose to balance things, right? But this is great. This is super easy. Okay. So we were feeling good. We got actually a sort of a very a proof of concept going, I don't know, like in a few weeks. That was almost 2 years ago. And okay. So one of the things that I always like to say is productivity and performance are the same thing, right? Some people will like try to be like, oh no, it's all about, that these are sort of different features. Depending on your perspective, I would say they're the same thing. So I would sort of high productivity framework, which right in this case would be Legion or Legate. You can get to a working solution quicker, and it probably scales quickly, right? You didn't do any parallelization work. So you have this amazing initial benefit. But then depending on the workload and what you're doing, right, as you try to push performance and performance higher, it might be the case that it becomes much, much harder to optimize if you you didn't start from the bare metal, and there might even be a crossover point at which you're just paying abstraction overhead. And it would have been easier, depending on your performance target, to have just said, I'm not using the high productivity framework because the abstractions are sort of getting in the way of the optimizations that I want to do. So right, to kind of illustrate the point, let's say I had 2 customers, and again, these are totally made up. Depending on your system, what you want to do. It could be that like even a 10% sort of loss of performance, maybe you don't really care because the optimization impact, right, is, less than sort of the whole cost of the project. Maybe you have some deadline, right? It's really critical that you get to like a 90% solution, in a few months, as opposed to just some sort of ongoing, you want it to be as fast as possible. Or maybe you have a customer that has a huge number and they really need to get that last 1%, because it's going to have a massive impact and there's no deadline, right? It's not like it's just an ongoing sort of engineering optimization. So, right. So depending on where you're targeting. So in terms of the LLM land, people really care about 1%. Right. So one of the things that sort of cropped up is dependency analysis and control replication overheads, particularly once we got to thousands of processes. There are hundreds of inputs and outputs for a lot of these LLMs. You have dozens of tensors. You have projection matrices, bias terms, MLP layers. You have parameters, gradients, and optimizer state for them. This gets really big. For a lot of the frameworks, they want to generate a bunch of scalar metrics. And they're sort of generated inside the task using like a nickel all reduce, and then I don't know, you write them out with feature maps, you do replicated writes, but they're sort of being written out everywhere. Because the most efficient way to kind of generate them everywhere was using this nickel all reduce. And so we ended up with like truly inscrutable scaling bottleneck because there are just so many small control messages kind of doing all of the control replication, the dependency analysis. So I will say the critical path analysis stuff that got added was super helpful to a point. So it did identify a bunch of scaling bottlenecks, but then at some point it just seemed like the network was melting. Like there was just no way to fix the issue. Like this was some hardware or software thing. So pipeline parallelism needs a well-defined task ordering. So the compiler has sort of statically seen everything that needs to execute, and it sort of has already derived an optimal schedule. Like I know the order that I want these things to run in. And if you start dynamically reordering them, it's actually not helpful in certain cases because it can start to be a gap. So like you see gaps in there like bubbles, and it might be the case that even if you could fill in a task, you'd actually don't want to because the sort of critical path task gets delayed because you started something in place. And if you had just waited a little bit, the critical path task could have started. But now you've put a bunch of extra work in there and you push the critical path out. So there's really no built-in mechanism for kind of like lightweight ordering of tasks to say, no, even if you think you can start, please don't, because trust me, the critical path task is coming soon, even if it's not there yet. Sort of another pain point, which was, kind of in the like 2 to 3% kind of issue. Sometimes you don't actually have any task parallelism. It's pipeline. And so you just have a sequence of tasks, and it can be that the next task depends on the previous task because you're accumulating gradients into a common buffer. And you end up with these little bubbles at the end of tasks in the pipeline. And they can add up. So tasks by default are not marked done until all of the data effects on the GPU are visible. So even if I'm submitting things onto the same stream, right, I could have just started the next task and the data effects would have been visible because they're all stream ordered. I still get a bubble in GPU utilization because the default behavior is no, just context synchronize, make sure all the data effects are done. Then you can start the next task. So there are tricks, at least on the you go directly to Rome, right, to kind of work around this issue. And but at least that was sort of difficult from trying to do things at the Legate level. Some other things that were a little bit difficult. So generally speaking, you don't always fully shard things in a lot of cases, like with data parallelism, or there are different sharding schemes where you want like partially sharded tensors. So it's sharded, but like you have replicated pieces in different ways. That gets you communication avoiding when you're doing tensor contractions later. As far as I know, it's not really technically valid to have these like replicated outputs or replicated rates in a sequential semantic. Mike did a lot of really great work to add support for that, so worked okay. The fully sharded and fully replicated is easily expressed in Legate, the sort of mid ground where you have like partially replicated that was actually not super easy to express at the Legate level. And particularly with fully replicated, you have tons of these like small either scalars or small tensors that you sort of generate. And you end up with like a lot of overhead from sort of rating them out in a fully replicated way. So that became problematic. Memory, that might have actually been I won't say which one is the biggest one. This was difficult to optimize. Right, so you create something, you pipeline it to the next stage. You're done with it on GPU 0, but it's still valid data, and I'm only reading it, and I might be sending it in different places. I might have to hold on to it and wait for backprop to come around later. And so first of all, even though you can't use different logical regions or things that are logically distinct, like that, just your memory just blows up immediately because you're not throwing away things that you don't actually need anymore locally. And then it's really critical to optimize, particularly these activations that get sent between GPUs. So for example, one example, which like GPT-3, you have 40 gigabytes of optimizer state. You basically have 30 gigabytes to work within your activations. You need to make really, really sure that once you're done with an activation on a GPU and you don't need to use it again, you throw it away. And you give that buffer back to the next wave of activations to be used. Okay, so where did we end up? So Legion has way more in it actually than we actually needed to use. So right, it's kind of going back to the core requirements. we wanted to be able to flexibly assign tasks and sharded tensors to different submeshes. Okay, so some sort of version of like mapping kind of the tasks easily and just kind of having the data movement happen for you. I'll talk about this sort of cross-mesh resharding communication primitive. You do need, like I said, execution dependencies for tuning task ordering. And ultimately, you would like to have sort of a very simple fine-grained control over sort of instance reuse and invalidation. Cross-mesh resharding is kind of like this. So most people will think of like MPI collectives. It's kind of in the same vein, but it's not like part of the MPI API. Basically, I have data that's sharded over some submesh, and it needs to become sharded over a different submesh. It could be the same sharding, so it's just like a point-to-point, but from like 0 through 3 to 4 through 7. Could be within the same thing, and I'm actually just permuting my shards. Or it could be I have actually a totally different sharding scheme, where I have to go from more sharded to less sharded. So these are sort of the different patterns that might end up depending on kind of what you're doing with your task pipeline. So you want the ability to do this asynchronous cross-mesh resharding. Like this is actually sort of a key fundamental piece in performance. You need this to be happening overlapped with computation on the GPU, and you don't want any of this communication exposed. If this communication gets exposed and blocks your computation, right, that's where you start to lose efficiency, right? And so, initially, like I said, Legate, I look great because all I do is I say how I want my data sharded. I say where I want the mapper to place it. And then all of, this data movement just kind of magically happens asynchronously in this realm in the background. But we can make some simplifications, sort of given the problem domain. So we're using control replication, and we have multi-controller execution. And because I have my compiler that kind of knows the global view of everything already, I really only need to do kind of like dependency analysis and dependency management on local shards. So I don't actually need nodes talking to each other to do dependency analysis. And then the only time that I actually need different processes to talk to each other is when I reshard data from one spot to another. So you're always operating on local shards. You're doing kind of this sort of single process version of the dependency analysis. And then because everybody kind of agrees on what needs to happen, they enter a reshard operation, and everyone sort of executes it. Some people no opt out of it, but everybody executes it because you're doing control replication already. Okay, great. I agree on what reshard needs to happen. And there's no separation of logical and physical arrays. If you create an array, those are buffers. There's no sort of mapping it to different memories later. And then I also don't need sort of a hierarchical or aliasing or slicing or anything like that. I just have tensors and I shard the tensors. But generally speaking, they're either replicated or disjoint, but I don't have anything else. So I can be a little bit simpler in terms of what I actually need to get to my perf. So this is still very much a draft, but I will say that the Realm event model made writing an asynchronous task-based framework kind of from scratch, like very easy, like less than a week, easy. If all you had was those requirements. So you define a mesh, you create some sharded arrays, you say I want to run a task on this mesh using that array. And then, okay, similar to Legion, I pull out my pointer. They all agree I have to reshard my data from source to destination, and then I run a task on my destination. So it's still sort of sequential code in that sense, right? Everybody is all executing the same control code in sequence. The only thing extra is, right, I knew that data had to be shuffled from point A to point B. Okay, and you can do some tricks with C++ data types to actually automatically create read-write versus read-only permissions. So the thing that we were able to add was there's a lightweight sort of ordering mechanism. I can have these preconditions on it. I can tag it as stream ordered, which means I don't use this heavyweight context sync mechanism. It just says, okay, if you're going to be submitting these things to the same stream, I can use different event preconditions. Everything's shared memory, so I actually can just directly pass arbitrary objects to the task. And yeah, so that's kind of where we ended up. So it's basically Legate / Legion, but sort of single process with an extra reshard primitive. So yeah, so some of the conclusion here was Legate Legion. I would say it was absolutely amazing for an 80% solution. Like I said, it was like literally a few weeks to implement pipeline parallelism in JAX. to get that sort of initial version going. It was only when we tried to squeeze out, the last 20%, try to go to much larger scales, that these problems sort of became apparent. And so in the end, the sort of, we needed to get to like the 99% solution, because if you leave any perf on the table, right, that hurts you in the context of LLM training, given the scale of it. So the 99% solution realm actually ended up being less engineering effort. And so in that sense, I would say sort of good or bad, it's entirely a matter of sort of customer and use case requirements, right? It really depends on what you need to get to, sort of what your deadlines are. Yeah. So